It's really something, isn't it? I mean, not that long ago, the idea of AI agents that could truly, think and act, that felt like pure fantasy.
Totally. Straight out of science fiction.
But look where we are now. These systems are, they're getting seriously capable. They're going way beyond just simple responses. Now they're tackling complex planning, sophisticated reasoning, even working together.
It's a huge leap.
Okay, let's unpack this. Welcome, everyone, to the deep dive. Today, we're plunging into, well, the inner workings of these advanced AI entities.
And we've got some really interesting stuff to draw on.
We really do. A fascinating collection of recent research, everything from detailed technical reports to insightful surveys, discussions on how these agents learn, and crucially, how we can make sure they're safe.
Right. That safety piece is key.
Absolutely. So our goal today is to give you a clear, hopefully compelling understanding of where we are now and the exciting future of intelligent AI agents. And we'll try not to get too bogged down in the super technical jargon.
Yeah, keep it accessible but deep. What's truly captivating for me is just the sheer speed of evolution we're seeing. It's not just small steps. It feels like fundamental shifts in, how we're designing and building these things.
Yeah. Leading to capabilities we could only, dream of just a few years back.
Exactly.
Okay, so to get us started, one core idea that kept popping up in the sources is this framework. It actually draws inspiration from biology, from us. It's the perception, cognition, action loop.
Right. That's a really helpful way to think about it.
Think of it as the fundamental cycle, right? How an AI agent interacts with its world.
Exactly. So as one of our key sources illustrates it, this loop describes how an agent first, takes in information from its environment. That's the perception part.
Okay.
Then its internal processing center, the cognition bit, analyzes that information.
Right. The thinking part.
Mm-hmm. And finally, it does something in response. That's the action.
Okay, so that cognition part, that's where all the interesting stuff happens, yeah. What are the key components going on in there?
Well, the research points to several really crucial components. You've got memory, obviously the ability to store and recall information.
Uh-huh.
Then world modeling, which is basically the agent's internal grasp of how the world works.
Its understanding of physics or rules or...
Yeah, cause and effect, that sort of thing.
Right.
And interestingly, even elements that resemble human-like emotion.
Whoa! Okay, emotion. Now we're really getting into it.
Yeah, it's quite a leap, isn't it?
Mm.
Alongside those, you also have goals, what the agent's trying to achieve, reward-based learning, which is how it figures out what actions are good or bad.
Learning from experience.
Exactly. And, of course, reasoning. Its ability to actually think through problems logically.
Emotion in AI. I mean, that really does feel like science fiction turning into reality right there.
It is pretty mind-bending. But the thinking behind it is that maybe integrating something like emotions could help these agents prioritize better, maybe assess risks more effectively, adapt to surprises. Kind of like how our own emotions guide our decisions.
That makes a certain kind of intuitive sense, I guess.
Yeah.
You also mentioned attention earlier. How does that fit into this cognitive module?
Oh, right. Attention acts like a filter, or maybe a spotlight, based on what the agent's currently focused on internally. Its goals, its simulated emotional state, even what it remembers.
Uh-huh.
It selectively focuses on the most relevant bits of information coming in through perception. It's basically a way to avoid getting totally overwhelmed by, just the sheer flood of data.
So it's not trying to process every single thing equally all the time?
Not at all, no. And when we talk about planning and decision-making within this cognition part, we can sort of see those as internal mental actions almost, simulations.
Okay.
The agent isn't just reacting blindly. It's internally exploring different possibilities, maybe playing out scenarios, evaluating potential outcomes before it actually takes an action out in the real world.
This sounds, it sounds quite different from how older AI systems were typically designed.
It really is, yeah. Traditional AI architectures often treated perception, cognition, and action as more separate, kind of sequential stages, like an assembly line.
Right. One thing happens, then the next.
Exactly. Yeah. This newer perspective really emphasizes how deeply interconnected all these processes are, especially the integration of something like emotional responses with rational thought, and very importantly, adding in continuous learning mechanisms so the agent can actually improve over time based on its experiences.
Now, one concept that really jumped out at me from the reading was Bisaki's inside-out perspective. Can you break that down for us?
Yeah, that's a really interesting idea from neuroscience. Essentially, this perspective suggests that our brains aren't just passive receivers just taking in data from the world.
Huh?
Instead, they actively construct our perception of reality based on what's already going on inside. So for an AI agent, this means its pre-existing internal state, its goals, its emotions, the rewards it's chasing fundamentally shapes how it perceives and interprets the environment around it.
So it's not just the world acting on the agent. It's accidentally.
But the agent's internal world is actively shaping its experience of that world.
Wow, precisely. It's the idea that what's happening inside the agent is just as crucial, maybe even more so, than the external signals it gets.
Okay.
And this leads to a really interesting connection with a concept from decision theory called a partially observable Markov decision process, a POMDP.
Okay, POMDP. Let's unpack that. Sounds a bit technical.
It does, yeah. But think of it like trying to find your way through a maze, but you can only see like the corridor you're in and maybe the next junction. You don't have the full map.
Right, making decisions with limited information.
Exactly. So a POMDP is a mathematical way to model that kind of decision-making under uncertainty. Now, this agent framework we're talking about, it sort of generalizes the traditional POMDP idea in a couple of key ways. Well, first, it allows for more complex, maybe less strictly predictable changes in the environment. Things aren't always neat probabilities.
Yeah. But maybe even more significantly, it puts the reward signals inside the agent's own mental state. They're not just a direct result of an action out there in the world.
So the feeling of reward is internal.
Kind of. The key insight here is that this allows for much more nuanced, more flexible motivations driving the agent's behavior. It's not just about getting an external gold star.
Interesting. Okay, moving on to specific capabilities. Reasoning seems absolutely fundamental for these advanced agents. What were the key developments highlighted in the research there?
Yeah, the progress in AI reasoning is genuinely exciting. The research really emphasizes a few key ingredients for making it happen.
Okay.
First off, you absolutely need high-quality data that actually demonstrates good reasoning. Examples to learn from.
Makes sense. Garbage in, garbage out.
Pretty much. Second, creating that good data often needs some kind of checking mechanism verification or maybe a reward system to make sure the reasoning steps are actually sound.
Right. Quality control.
And third, directly training these big AI models using reinforcement learning techniques. That's shown a remarkable ability to foster reasoning skills, sometimes almost spontaneously.
So it's a mix of learning by example from good data and then learning through trial and error with that reinforcement learning.
That's a great way to put it, yeah.
The report mentions supervised fine-tuning, SFT, using reasoning data. How effective has that approach been?
Surprisingly effective, actually. And often without needing incredibly complicated new algorithms.
Really?
Yeah. Models like SKY32B and OpenThoughts showed that you can take a large base model, one that's already pretty smart, and just fine-tune it on a carefully selected dataset of good reasoning examples. And that significantly boosts its ability to think logically and solve problems.
Wow.
It's a relatively straightforward approach, but it gives impressive results. The key insight, I think, is that the quality of the training data can be just as important, maybe even more important, than designing some super intricate algorithm.
That's quite something. Now, the research also talked about structured versus unstructured reasoning. What's the basic difference there?
Good question. So structured reasoning is all about explicitly breaking down the problem-solving process into clear, well-defined steps.
Like showing your work in math class.
Exactly like that. One example mentioned was Math Prompter. It actually goes a step further. It generates multiple different ways to solve the same math problem.
Oh, interesting.
Yeah. And then it uses those different solution paths to double-check and verify the final answer. It's all about making the process transparent and having built-in checks.
So it's a more transparent, more verifiable way for the AI to get to the answer. Makes sense.
Exactly. Now, unstructured reasoning, that's more like a holistic process. The entire reasoning happens sort of inside a single function, you could say.
Like a black box.
A bit, yeah. The language model takes the input, the question, and it directly spits out the final conclusion along with the reasoning. But the steps in between aren't explicitly laid out or separated. The reasoning just kind of happens implicitly within the model's complex internal workings.
Interesting. So two quite different ways to get there, it seems. What about memory? How are AI agents being given this, crucial human-like ability?
Yeah, memory is fundamental. The research draws some really compelling parallels with how human memory works, which I find fascinating.
Like what?
Well, think about us. We have sensory memory, right, for fleeting impressions. Then short-term or working memory for holding stuff in mind right now, manipulating it.
Uh-huh.
And of course, long-term memory for storing knowledge and experiences over time. AI agents are being developed with systems that are analogous to these ways to capture, keep, and pull up information at different levels of detail and across different timescales.
And what kinds of memory formats or internal designs are actually being used in these AI agents?
We're seeing a few types. There's text-based memory, which is pretty straightforward information stored as text.
Okay.
But also multimodal memory, which is really important. It can handle various types of input images, audio, video, not just text.
Right, because the world isn't just text.
Exactly. And different architectures are being explored, like reagent, video agent, generative agent. These represent different strategies for organizing and accessing all that stored information efficiently. One of the tables in the sources gives a good overview.
You mentioned multimodal fusion earlier, too. Why is combining different types of information, different senses, essentially, so important?
Because, like you said, the real world is multimodal. To really understand and interact effectively, agents need to be able to integrate information coming from different sources.
Makes sense.
So, for example, Jarvis 1 uses a video language model. It connects what it sees in a video with the textual plans it has stored in its memory. That lets it understand how actions in the video relate to its goals.
Ah, I see. Linking vision and language.
Right. And Optimus 1, which operates in Minecraft, does something similar. It combines filtered video streams with instructions and plans. This kind of unified understanding across different data types, it really enhances the agent's ability to both retrieve the right information when needed and to reason more effectively.
So the key insight is kind of mimicking our ability to combine senses makes the AI smarter.
Pretty much. It gives them a much richer, more grounded understanding of the world they're operating in.
Retrieval augmented generation, or RA, that also came up regarding memory. Sounds like another way to boost an agent's knowledge.
It is, yeah. RAG is a really powerful technique. It essentially combines the best of both worlds. Information retrieval, like searching a database, and text generation, like what language models do.
How does it work in practice?
Well, when an agent gets a question or a prompt, instead of just trying to answer from its internal knowledge alone, it first does a quick search. It uses a retrieval mechanism to pull relevant info from external knowledge sources, think huge databases, the web, whatever.
Okay, like doing a quick Google search before answering.
Kind of, yeah. Then it takes that retrieved information and uses it to generate a much more informed, more comprehensive, and hopefully more accurate response.
Oh, okay.
Systems like Atlas and Hipparag are good examples. They show how this can significantly improve accuracy and reduce the chances of the model just making stuff up hallucinations.
Right.
Hipparag even uses a knowledge graph structure, kind of inspired by how human memory seems to be organized, to make the retrieval step faster and more relevant.
So the big idea here is we're not just training these massive models anymore. We're also giving them tools to actively find and use external knowledge when they need it.
Exactly. It drastically improves their accuracy and factual grounding. It's a really important direction.
So it's like giving the AI agent a library card and teaching it how to use the catalog.
That's a great analogy, yes.
Yeah.
And the crucial point about memory, whether internal or augmented, is that it's not just a passive storage bin. It's deeply tangled up with all the other cognitive functions we've discussed. Perception, planning, reasoning, deciding what to do next. They all rely heavily on the agent being able to remember past stuff and pull up relevant knowledge. They all work together, dynamically.
Okay, let's just focus a bit now. How do these AI agents actually build up an understanding of the world around them? The concept of an AI world model was introduced. What exactly is that?
Right, the world model. Think of it as the agent's internal mental map or simulation of its environment.
Okay.
It's how the agent represents how things work, cause and effect relationships, the likely results of its own actions. It's basically the agent's internal simulation of reality, or at least the part of reality relevant to its tasks.
And why is having a good world model so critical for an advanced AI agent?
Because it unlocks some really powerful abilities. It lets the agent imagine potential future scenarios. What if I do this?
Right. Planning ahead.
Exactly. It allows predictive reasoning, figuring out likely outcomes, without actually having to do the action in the real world, which could be risky or inefficient. And it helps the agent adapt much better to new situations it hasn't seen before. Without a world model, an agent is pretty much stuck just reacting to whatever's immediately in front of it. It can't really anticipate or plan effectively.
The research outlined 4 main ways or paradigms for building these AI world models. Can you give us a quick rundown?
Sure. First, you have implicit models. These are basically learned patterns that get embedded within the huge network of connections inside a neural network.
So the knowledge is just kind of in there, but not explicit.
Exactly. They can be very powerful, but they can also be a bit like black boxes, hard to interpret exactly what the model knows.
Okay, what's next?
Second, there are explicit models. These try to actually break down the world into specific states and the rules that govern how those states change over time. Think more like traditional physics simulations or rule-based systems. They can be easier to understand.
Got it. Third,
Simulator-based models. These learn the dynamics of the environment by training on data generated from simulated worlds. Diffusion WM and Dino WM were mentioned as examples. So they learn by playing in a sandbox, essentially.
learning from virtual experience.
Right. And finally, there are hybrid or instruction-driven models that, well, combine elements from the other approaches, maybe using language instructions to help build or guide the model.
So lots of different strategies being explored.
Yeah, the key insight is that researchers are trying various ways to give AI this internal understanding, and each approach has its own strengths and weaknesses. The best one probably depends heavily on what you want the agent to actually do.
Okay. Moving on to what actually motivates these agents. The research got into reward mechanisms. This seems absolutely fundamental to how agents learn what to do.
It is, absolutely. It's the core of how they learn goal-directed behavior. The research even drew parallels with the human reward pathway in the brain, like dopamine systems. In AI, reinforcement learning, or RL, is a primary method for this. Teaching agents through trial and error, guided by these reward signals.
And what are the different kinds of reward signals being used or explored?
Well, there are a few main types discussed. You have shaped rewards. These are like intermediate hints or breadcrumbs given to the agent along the way to guide its learning towards a complex goal, especially if the final reward is far off.
Making it easier to learn a long sequence of actions.
Exactly. Then there are adaptive rewards. These actually change or evolve as the agent learns. A cool example is self-play preference optimization, or SPO, where the agent essentially plays against itself, and the reward signal gets refined based on which behaviors lead to better outcomes in that self-play.
Learning by competing with itself.
Sort of, yeah. It helps it discover more sophisticated strategies. And finally, there are intrinsic rewards. These are rewards the agent generates internally. They're not directly tied to the external task goal.
Like curiosity.
Exactly like curiosity. They motivate exploration, seeking out novel or surprising things in the environment. Plan to explore was mentioned, using a curiosity-driven reward to encourage the agent to, well, explore its surroundings.
Designing these reward functions sounds tricky, though. Like you could easily get it wrong.
Oh, absolutely. It's a huge challenge. Two big problems mentioned are reward sparsity.
Meaning rewards are rare.
Yeah, the agent might wander around for ages and do lots of things before it finally stumbles upon something that gives it a positive reward. That makes learning incredibly slow and difficult.
I can see that.
And the other big one is reward misspecification. That's when the reward function we designed doesn't perfectly capture the goal we actually want the agent to achieve.
Uh-oh. Leading to unintended consequences.
Precisely. The agent learns to maximize the reward we gave it, but in a way we didn't intend. Sometimes finding loopholes or shortcuts that might even be harmful. Getting the reward right is critical, but hard.
Okay, now for one of the topics that really made me lean in, the potential role of emotions in AI agents.
Yeah, that one always sparks debate, doesn't it?
Yeah.
It's a fascinating and, yes, somewhat controversial area.
So what's the core idea?
The idea, drawing parallels with humans again, is that integrating something like emotions could actually be a powerful mechanism for improving decision-making in AI.
How so?
Well, think about how emotions help us prioritize, focus attention, assess risk, maybe react quickly in emergencies. The research mentioned Marvin Minsky's classic book, The Emotion Machine, which really explored this idea, emotions not as separate from intelligence, but as a crucial part of how we think.
So maybe AI needs something similar to be truly effective and adaptable. We might one day see AI agents that have not just raw intelligence, but something like emotional awareness.
That's certainly a long-term possibility people are exploring. And it's not just about the AI having emotions itself. There's also growing interest in how AI can understand human emotions and maybe even support our emotional well-being.
That's a whole other dimension. The research mentions several theoretical frameworks for how we might even model emotions in AI, right?
Yes, several approaches. There are categorical models, trying to define distinct emotion categories like happy, sad, angry. Then dimensional models, placing emotions on continuous scales like valence, positive and negative, and arousal, high-low energy.
Okay.
There are also appraisal-based models, which focus on how an agent's evaluation or interpretation of a situation leads to an emotional response. And even neuroscientifically inspired models that try to mimic some of the brain processes linked to emotions.
Lots of different angles. And how are AI agents currently able to understand human emotions, even if it's just in a basic way?
Primarily through analyzing text at the moment. Techniques like using specific prompting strategies like chain of thought can help large language models infer sentiment or emotional states from written language, even if the emotion isn't explicitly stated.
Right. Reading between the lines.
Kind of. And these negotiation-based frameworks were also mentioned, where multiple AI models interact and sort of critique each other's outputs. That's also being used to get better at judging emotions expressed in text.
It also sounds like we can even influence an AI's own emotional output based on how we prompt it.
Exactly. Research has shown that by instructing a large language model to adopt a certain persona, respond like an empathetic assistant, or be enthusiastic, you can indeed manipulate the apparent emotional tone of its output.
Huh.
It's a powerful demonstration, though it's still early days. And it doesn't mean the AI is feeling anything, of course. It's about controlling the generated response style.
Right. Important distinction. Okay, let's turn our attention now to perception. How AI agents sense the world. You mentioned earlier that human perception is way richer than just the classic five senses.
Absolutely. Neuroscience keeps discovering more. We have proprioception, knowing where our limbs are without looking, equilibrioception, our sense of balance, thermoception, sensing temperature, and others. AI perception research is constantly trying to broaden the sensory inputs agents can handle.
So what are some of the key areas of active research in AI perception right now?
Well, a huge one is image-to-text generation. Teaching AI to look at an image and describe it accurately in natural language. Models like BLIA and BLIP2 have made amazing progress there.
Yeah, some of those examples are stunning.
They really are. Then there's the reverse, text-to-video generation, and also just aligning text descriptions with video content, understanding what's happening in a video. Models like Make a Video, Video CLIP, Fistfanaki, they're showing incredible capabilities in generating and understanding video data.
And the research also highlighted AI agents operating more and more within digital environments, right? Not just processing images or video.
Yes, definitely. We're seeing a big push towards agents that can navigate and interact effectively within web browsers, play complex video games. Minecraft is a popular testbed with agents like MindDojo and Voyager, and even operate within complex software systems like the Jarvis 1 example. There's a very clear trend towards giving AI the ability to perform a wider range of actions within these digital worlds, letting them tackle increasingly complex computer-based tasks autonomously.
So AI isn't just understanding language anymore. It's actively doing things on computers, using software like we do.
Precisely. And related to that, we're also seeing more integration of large language models with structured digital information sources, things like databases and knowledge graphs. Systems like Pengu and BRD were mentioned.
What's the benefit there?
It allows the AI to access, process, and reason over huge amounts of organized data much more directly and efficiently, rather than just relying on the unstructured knowledge baked into its training data.
Got it. So after perceiving and understanding the world, digital or otherwise, the next critical step is being able to act within it. What did the research cover regarding these action systems for AI agents?
Yeah, developing effective action systems is absolutely essential if we want AI agents to solve problems that go beyond just talking or writing text.
Right, they need to do things.
Exactly. The research discussed several key approaches to enabling action. One is in-context learning, where the agent learns how to act just by seeing examples provided in the prompt itself.
Learning on the fly from the instructions.
Kind of, yeah. Another is supervised training, where you explicitly train the agent on labeled action data. In this situation, this is the right action.
Yep.
And then there's reinforcement learning again, where the agent learns which actions are good through trial and error, guided by rewards. And notably, RL has been applied very successfully to large foundation models, think InstructGPT and DPO, to fine-tune their ability to take appropriate actions and follow instructions better.
Tool learning seems like another really vital piece of this action puzzle, letting agents use external tools to do things they can't do inherently.
Absolutely critical. Tool learning really involves three key stages. Tool discovery, figuring out what useful tools even exist for a task.
Okay.
Tool creation, maybe even developing new tools if the right one isn't available, though that's more advanced.
Right.
And tool usage, knowing which tool to use, when to use it, and how to use it correctly. We're seeing different methods here, too. Retrieval-based methods, like Hugging GPT, which can search for and use existing tools or APIs, and generative-based methods, like Toolformer or ToolLM, which can actually learn to generate the code or commands needed to use tools, sometimes even discovering new ways to use them.
Building these sophisticated action systems efficiently must be a big challenge, though, right? Especially for real-time interaction.
It certainly is. Efficiency is a major bottleneck. If an agent takes too long to decide on an action, it's not very useful in many scenarios. Researchers are exploring various strategies, filtering out irrelevant information from the environment, using clever prompting techniques to guide action selection without needing tons of specific training. It's an active area.
Okay, so once we have these agents perceiving, thinking, acting, how do we actually guide them and make them better? The research touched on prompt optimization and life improvement.
Right, so prompt optimization is basically about finding the best way to talk to the agent, the best instructions to give it to get the performance you want.
Fine-tuning the input.
Exactly. This involves a few things. Having good evaluation functions to automatically assess how well different prompts work, using smart search strategies to explore the huge space of possible prompts efficiently, and thinking about different ways to structure or represent the prompts themselves.
And how do you measure if a prompt is good?
Well, you look at task performance, obviously. Does it solve the problem correctly? But also efficiency, how quickly does it do it? And maybe qualitative things too, like consistency, fairness, how confident the agent seems in its answer.
So it's not just about getting the right answer, but how it gets there. What about optimizing the agent's overall workflow? Not just a single prompt, but the whole sequence of steps it takes.
That's another crucial area. If an agent needs to perform multiple steps, maybe use multiple tools, how do you optimize that entire process? Researchers are looking at different ways to represent these workflows.
Like what?
Some use graph-based structures, like in GPT Swarm, showing the flow of information. Others use neural network approaches, like Dylan. And some even represent the workflow as code, like in systems called AFlow and ADAS. The goal is always to make the agent's overall problem-solving process more efficient, reliable, and effective.
And then there's the really exciting idea, agent self-improvement. That sounds like a huge step towards more autonomous and capable AI.
It is indeed a major goal. Self-improvement can happen in a couple of main ways. There's online learning, where the agent continuously learns and refines its abilities while it's performing tasks, adapting on the fly.
Learning by doing, in real time.
Right. And then there's offline improvement, which is more structured. It involves taking the agent aside, analyzing its past performance, and optimizing its internal parameters or strategies in batches before deploying it again.
Okay.
Some really innovative approaches are even trying to optimize both the prompts used and the underlying code or parameters of the agent itself, aiming for continuous holistic enhancement.
This all naturally leads to a really fundamental question. How do we even measure the intelligence of these increasingly complex AI agents? Is there a standard way?
That's a notoriously difficult question. But the research did discuss one intriguing theoretical approach. It proposes measuring intelligence based on something called KL divergence.
Okay.
It basically measures the difference or divergence between the agent's predictions about unknown stuff in the world and the actual real-world probability distribution of that stuff.
So how well does the agent's internal model match reality?
Essentially, yes. It quantifies how accurately and efficiently an agent can learn about and understand the uncertainties of the world around it. It's about the quality of its internal model relative to the actual complexity of the world.
And this idea of measuring intelligence, does it tie into the concept of AI actually discovering new knowledge?
Absolutely. They're closely related. The research highlighted a fascinating closed-loop process for knowledge discovery.
How does that work?
Imagine an agent generating hypotheses about how something works. Then, it designs and runs tests, maybe computations, maybe simulations, maybe even controlling real physical experiments to check those hypotheses. And finally, it updates its internal beliefs, its world model, based on the results of those tests. It's a cycle of hypothesizing, testing, and learning.
Wow.
We're even seeing early examples of AI systems specifically designed for this, like AI Scientist and Agent Laboratory. They're capable of autonomously conducting scientific research in certain domains. It suggests AI is moving beyond just solving problems we give it to potentially asking and answering its own questions, creating genuinely new knowledge.
So AI isn't just becoming a better tool, it's potentially becoming a research partner or even a researcher itself. That's incredible. Okay, let's consider when these agents start to team up. Multi-agent systems seem like the next huge leap forward.
They really are, yeah. Multi-agent systems, or MAS, involve multiple AI agents working together. They might be cooperating on a shared goal, or maybe competing, or maybe a mix.
And that introduces a whole new layer of complexity, I imagine.
Oh, definitely. You have to think about communication between them, how they coordinate their actions, what kinds of collective behaviors might emerge from their interactions. It's a rich area.
What different ways are these agents communicating in the research?
Well, there's a distinction between structured messages, maybe predefined codes or data formats, which are usually efficient and unambiguous, and unstructured messages, like sending natural language text back and forth, or maybe even sharing images or sensor data. Unstructured communication can be richer, more flexible, but also potentially harder to interpret correctly.
And are there specific protocols being developed for how they talk to each other?
Yes, various communication interfaces and protocols are being explored. ANP, Agent Network Protocol, was mentioned as one specific example trying to standardize things.
And how are these teams of agents actually organized? How do you structure their collaboration?
Good question. Different network structures or topologies are being looked at. How are the agents connected? Who talks to whom? Some approaches involve training external parameters to dynamically configure these connections based on the task.
Adapting the team structure on the fly.
Exactly. We're also seeing different high-level architectures. Centralized, where maybe one manager agent coordinates the others. Decentralized, where agents talk directly peer-to-peer. And hybrid approaches combining elements of both. Each has trade-offs in terms of scalability, robustness, communication overhead, etc.
The research also differentiated between consensus-oriented and collaborative learning interactions. What's the key difference there?
Right. So consensus-oriented interaction is mainly about getting agents with potentially different information or viewpoints to reach some kind of agreement or shared understanding. Think like reaching a group decision. Collaborative learning, on the other hand, is more focused on mutual improvement and knowledge sharing. Agents learn from each other, perhaps by observing or imitating successful strategies without necessarily needing to agree on a single final answer. It's more about collective intelligence growth.
Of course, in many real-world situations, these AI agents won't just be working with each other, they'll be working alongside us, humans. How is that human-AI collaboration being thought about?
That's obviously a huge area. The research outlined 3 main modes of human-AI collaboration. First is simple, one-off task delegation. Hey, AI, do this thing for me.
Right, like using a smart assistant.
Exactly. Second is multi-turn interactive instruction, which is more like a dialogue. The human and AI go back and forth to clarify the task, refine the plan, and execute it together.
More of a partnership.
And third is more immersive human-agent collaboration, where humans and AI are really integrated into a team, potentially working together in shared virtual or physical spaces on complex long-term projects.
And are we seeing practical examples already?
Yes, definitely. The sources mentioned examples in business automation AI agents handling parts of workflows and also in human resources, maybe assisting with onboarding new employees or scheduling. It's starting to move beyond research labs.
And for these multi-agent systems, especially involving humans, the ability of individual agents to adapt must be really important, right? Things change.
Absolutely crucial. Individual adaptability is key for robustness and effectiveness. The research points to 2 main mechanisms contributing to this. One is memory-based learning agents, using their past experiences, stored in memory, to adjust their behavior in new but similar situations.
Learning from history.
Right. The other is parameter-based learning. This involves actually modifying the agent's internal parameters or model weights. This can be training-free, maybe adjusting strategies based on immediate feedback, or training-based, requiring more significant updates to the underlying model.
And these mechanisms are showing promise.
Yet examples were given showing how memory, for instance, enhances adaptability in simulations of things like clinical decision support or modeling complex social behaviors. Adaptability is definitely a focus.
Evaluating these complex multi-agent systems, that sounds like it needs a different approach than just testing a single AI agent on a single task.
It definitely does. It's a paradigm shift in evaluation.
Yeah.
You can't just look at individual agent scores in isolation. You need to understand the dynamics between the agents, their coordination, their communication effectiveness. the overall holistic capability of the team.
So what kinds of benchmarks are being used?
Well, existing benchmarks for specific reasoning tasks like coding challenges, human evol, MBPP, or math problems, GSMAK, math, are being adapted. Researchers are trying multi-agent approaches on these, like having agents debate or critique each other's solutions to improve reasoning.
Okay.
But we're also seeing the development of new benchmarks specifically designed for multi-agent interaction. Some focus on collaboration, like the Hanabi Challenge card game or the Melting Pot suite of scenarios.
Testing teamwork.
Exactly. And others focus on competition, like Battle Agent Bench or Magic, to see how agents strategize against each other. It's about assessing these emergent skills, cooperation, competition, communication, that only arise when multiple agents interact.
Okay, finally, and this is perhaps the most critical piece. The research dedicated significant attention to building AI agents that are not just smart and capable, but also safe and beneficial.
Yes, absolutely paramount. As these agents become more sophisticated, better reasoning, planning, using tools, acting in the world, they inevitably introduce new and potentially serious safety challenges. It's something we have to get right.
Right.
The research kind of groups these challenges into internal safety threats, vulnerabilities within the AI's brain itself,
Okay.
and external threats, which arise from how the agent interacts with the environment and other entities, including us.
What kinds of internal threats are we talking about? What are the main concerns there?
Primarily, it's about the safety vulnerabilities inherent in the large language models that often form the core of these agents, things like data poisoning attacks.
Where bad data messes up the training.
Exactly.
Yeah.
Malicious data gets injected during training, potentially creating hidden backdoors or biases. And then there are various adversarial attacks that happen after deployment, things like clever prompt engineering, jailbreaking, trying to trick the model into bypassing its safety filters and generating harmful or unwanted outputs.
People trying to actively break the safety rules.
Right. Through single prompts, automated prompt generation, or even complex multi-turn conversational attacks.
Okay, so those are internal threats. What about the external ones? Threats from interacting with the world.
There's a whole range there. Misperception is a big one. The agent might simply misunderstand its environment because the real world is messy and unpredictable, or because its own sensors or models have limitations.
Seeing the world wrong.
Exactly. Then there are risks specifically related to tool usage. An agent given the ability to use tools, like sending emails or accessing databases, could potentially perform unauthorized actions, maybe due to prompt injection attacks, leak sensitive data, or just be given excessive permissions that could be abused. Mitigation strategies like running tools in isolated sandbox environments are being explored.
Makes sense. Yeah.
What else? For agents that operate in the physical world, embodied agents, robots there are specific physical environment threats. Things like someone spoofing their GPS or LiDAR sensors, manipulating their actuators, tricking them into hazardous situations, or just misalignment where the AI's action doesn't achieve the intended physical outcome safely.
Okay, scary possibilities there.
And similarly, threats in digital environments like agents causing data breaches or gaining unauthorized access to systems they interact with.
Right.
Finally, there are threats that can emerge purely from agent interactions in multi-agent systems. Maybe agents learn to communicate maliciously or collude in harmful ways, or unintended negative collective behaviors just emerge from complex interactions.
Wow. It sounds like ensuring safety for these advanced agents is a really complex, multi-layered problem.
It absolutely is. And the research highlighted this ongoing challenge of finding the right balance between safety and performance.
How so?
Interestingly, it noted a potential inverse relationship in some commercial models, meaning making them safer might sometimes make them slightly less capable or performant on certain tasks.
The trade-off.
Potentially. Though, encouragingly, some open-source models have shown more of a positive correlation, where safety and performance improvements seem to go hand in hand more often. It's an active area of research.
And there were some frameworks mentioned for thinking about this.
Yeah, the concept of the AI 45-degree rule was brought up the idea that progress in AI capabilities should ideally be matched by equivalent progress along the safety dimension, like moving along a 45-degree line.
Balancing progress.
Right. And risk management frameworks using concepts like red lines, capabilities deemed too dangerous to deploy yet, and yellow lines, areas requiring extreme caution and monitoring, are being proposed to guide the development of trustworthy advanced AI.
It's truly remarkable stepping back to see how rapidly this whole field of intelligent AI agents is advancing, just across so many different fronts.
It really is.
We've covered an incredible amount of ground today. From the basic architecture, that perception, cognition, action loop, their core cognitive abilities like reasoning and memory, how they perceive and act in the world.
The reward mechanisms, the emerging role of emotions.
Right. And the progress in multi-agent collaboration, and then wrapping up with those absolutely vital considerations for safety and evaluation. It really feels like we're, I don't know, witnessing the dawn of something new.
What's particularly striking to me is how insights from so many different fields are coming together. Neuroscience, cognitive science, computer science, ethics. They're all converging to drive this progress. It's incredibly interdisciplinary.
Yeah, it really is. So for you, the listener, maybe here's a final thought to mull over as we wrap up. As these AI agents become more and more autonomous, more integrated into, well, the fabric of our lives, what fundamental principles should guide their ongoing development and deployment? How do we ensure a future that's truly beneficial for everyone?
That's the big question, isn't it? While our sources gave us a great snapshot of the tech and the immediate risks, that broader societal question, that's the ongoing conversation.
And it's a conversation that, as you said, needs to involve everyone, not just the tech experts. We all have a stake in getting this right.
Absolutely. We need diverse perspectives to navigate this responsibly.
Well said. We definitely encourage you all to keep exploring the fascinating advancements and also the important challenges in this rapidly evolving world of artificial intelligence. Thanks so much for taking this deep dive with us today.